All right, these are the nature of science slides. So we start this off by asking a question. What height was this photo taken from? Now, what would be a good guess? Would you say 10 feet? I mean, probably not. It was taken a lot higher than 10 feet. What about 10 miles? Well, you know it's going to be lower than 10 miles. What about 500 feet? And if the helicopter or whatever was taking this photo went up 1 foot, would you say it was 500 feet? Or 501 feet? Like, do you have the knowledge to be able to do that? Same thing about weight. If you look at this person and say, how much does this person weigh? Would you say 100 pounds? You probably say, well, no, I know this person weighs more than 100 pounds. What about 500? No, this person weighs less. What about 180 pounds? Now, let's just say this person had a large lunch and you come back and see this person later. Would you be able to look at that person and say, oh, that person weighs 181 pounds now? Same thing with crowd size. What would be a good guess? 500? No, it's more than 500. What about 50 million? Probably less. Maybe 500,000? Okay, yeah. And if one person were to leave, would you be able to say there's 499,999? Well, probably not. Now, in all of these examples, you were doing the measuring, right? So to be more accurate, you would need an altimeter, a scale, and a turnstile, right? They are more accurate than you doing the measuring. And that brings us to resolution, which is the smallest interval that can be measured by an instrument. So on the top, the ruler is 1 meter, but on the bottom, it's zero point 0.1 meters because it's divided a meter into 10. So if you look at an analog stopwatch, every one of those tick marks is 1/10 of a second. If you look at the digital one, well, the last decimal point is going to be 1/100th of a second. So the resolution of the stopwatch, well, that last decimal point is 0.01 seconds. So that is the resolution. So the resolution of this meter sticks, well, it's divided into millimeters. So that would be the resolution, 1/1000th of a meter. Now, you can estimate even further on analog instruments. That is what we call an uncertainty digit, or that doubtful digit. And it's an estimate, a measurement with a higher resolution. We call this our level of uncertainty or doubtful digits. And can only be done with analog instruments. So if we look at the ruler below, the resolution is 0.1 meters. Now you can make an estimate as to what that next digit would be. So you can estimate to about the hundredth of a meter. You might say the length is 0.46 meters. That 4 is certain, but that second digit 6, that's going to be doubtful. Now, if we did one where the resolution is 0.01 meters, you can make an estimate as to that next one. You could say the 0.35 are certain, but that third digit 8 is doubtful, but you can make an estimate. And once again, this can only be done on analog instruments. So now let's talk about significant figures. There's the number of digits in a value, often a measurement that contribute to the degree of accuracy of the value. So these are the rules. 1 through 9 are always significant. Leading zeros are never significant. Captive zeros are always significant figures, and trailing zeros are only significant figures if there's a decimal point. So here's the importance of significant figures. So if you look at this, if you look at somebody and say, well, that person's about 180 pounds. Well, using our rules, these are two significant figures because that zero is just a placeholder. We don't know if that's accurate. But if that same person steps on a scale and it says 180.0, well, those zeros aren't placeholders anymore. Those are accurate. That's why this number has four significant figures. Same thing with the crowd size. If you look at a crowd size and say there's about 10,000 people there, all those zeros are placeholders. We don't know if they're accurate. It only has one significant figure. But if you look at like a turnstile data and it says there's 10,001 people in this amusement park or in this crowd, all of those are going to be significant figures. All of those are accurate. It has five significant figures. All right, so when we're dealing this with math, we don't really have to deal with the rules of adding or subtracting that much, but multiplying or dividing, well, your answer can only be as accurate as the number with the least number of significant figures. That's the least precise value in terms of multiplication and division. You look over to the right, you can see here there's like these are okay, those are added, but this one is three significant figures. You multiply by something that's four significant figures. Your answer can only be accurate to three significant figures. So here's the example that I use, right? So let's just say you're trying to find out how fast your friend is in meters per second. You do not have a measuring tape, but you have this person start estimate to be about 100 meters back. You all could figure out about how far 100 meters is. You know it's going to be about like the length of a football field. You could estimate that. You've been on a track before. You could estimate that. Then you say, all right, you draw a start line and an end line where you think about 100 meters is, and you say, on your mark, get set, go, and this person runs the length in 13.63 seconds according to your phone. So here's how we calculate mean speed in meters per second. You take the distance divided by the time, and this is what you get. Now, the least accurate measurement is what you use to measure the length of that field. You just used what you guesstimated, right? That 100 meters. That answer only has, that 100 meters is only one significant figure. We didn't measure it out with a measuring tape and say, yep, this is 100.00 meters. No, we just estimated that. That 13.63, that's going to be very accurate, but our least accurate answer is what we use to measure the distance. So using our rules of significant figures, you could only have one significant figure in the answer, and 7 meters per second. So this would be an example, right? If I'm trying to measure this, and you can't really see this, but this is a meter stick, right? And it's not divided into anything else. It's just 100 centimeters. You could probably say this thing is about 20 or 30 centimeters. You can't say it's 27.839 centimeters. We do not have that resolution. Now, your answer only has one significant figure. If we do this again, now our resolution is 1/10 of a meter or 10 centimeters. Now, it does have an uncertainty digit, so you can say about 22 centimeters, right? You can look at this and say there's 22. Now your answer is two significant figures. Now, if we increase our resolution even more, divide it into 0.01 meters or 1 centimeter, you can say this is about 22.5 centimeters, and now I have three significant figures. Now, here's the thing. If you can record it, right? So in this one, it does have an uncertainty digit. You would say this is about 23.50 centimeters. So four significant figures. Now, 23.5 centimeters would be wrong because you could have said 23.50 centimeters based upon the resolution of this instrument. Include that uncertainty digit. If you can record it down, if you can be that accurate, if you have that resolution, put it, even if it ends in a 0. So now let's talk about accuracy. The accuracy of an experiment is a measure of how close the experimental result comes to the accepted or actual value. Think about throwing darts at a dartboard. It's how close are these darts to the bullseye. So now let's talk about precision. That's how reproducible that result is, or how close the darts are to each other. So just to sum it up, how close the darts are to the bullseye is accuracy. How close the darts are to each other, that is precision. So we did the drop the ball experiment in order to demonstrate this. So nobody had a meter stick to measure it out. You had to measure it with your, based on what you thought 4 feet was. This would affect your accuracy because you don't know exactly where 4 feet was. Now, to make sure that your group was dropping it from the same height, you had to mark off where it is. This would affect your precision. Even if you dropped it from above your head, well, that's not going to be an accurate representation of where 4 feet is, but it would be precise because you're dropping it from the same spot. Now, how you measure it can affect both. If you do it the same way over and over again, that's going to affect precision. Now, how you do it will affect accuracy. If you have the same person dropping the ball and starting the time, then that time would start as close as possible to when that ball was released. So accuracy and precision are affected by errors, and we learned about systematic and random errors. Now, systematic errors are usually caused by defects in measuring instruments. They are reproducible. They shift the data in one direction or another. They cannot be reduced by repeating. So let's think about a scale that always starts offset by 10 pounds, right? Now, if that person steps on and off that scale, that error does not go away. And if we took data of the weight of everybody in the room, all that data would be shifted one way. It would be shifted 10 pounds heavier. It can be eliminated, and we can get rid of this by getting another scale or fixing the scale. And they lead to poor accuracy, right? That scale would read the same every single time. It's going to be precise, but it's not going to be accurate or close to that accepted value. Also, parallax reading is the same one. If you're reading a measurement off center, you're going to read it not close to that accepted value. So they can be eliminated by reading the device correctly. Now, random errors are statistical fluctuations in either direction in the measured data from uncontrollable causes. It's the experimenter's inability to take the same measurement in exactly the same way to get the same number. They are not reproducible. They usually shift the data in both directions. They can be reduced by averaging over a large number of observations. That leads to poor precision. And think about dropping that ball. Well, Uh, if you do that, like those numbers were kind of like all over the place. This is an example of random errors, and that was that answer. Random errors. Now we reduced it, like we can't get rid of it. We reduced it by averaging, by taking five results and averaging. Now, systematic errors, that would be the fact that you didn't know where 4 feet was. That's going to affect that accuracy of it, right? So that was one of those. Now, if we were to conduct this experiment again, you probably need a meter stick to increase the accuracy so you knew exactly where 4 feet was. And what would you need to in order to increase the precision? Well, eliminate the human reaction time. We were starting everything on human reaction. We said you're going to start the time when you see this ball drop. You're going to stop it when it hits the ground. If you were to have like a photo gate, that would reduce that random error. And you look at this when this same experiment was done with the photo gate, you'll notice those times are a lot closer. Now, there's still some random error, and there's still some systematic error. Notice that all these values are lower than the accepted value of 0.51. That could probably be because maybe the photo gates weren't exactly 4 feet apart. Maybe the marble was started just a little bit above where that line to start it. Yeah, so there's still systematic errors and random errors, but they're being lowered once we start getting rid of the human reaction. All right, and that brings us to our final thoughts. Remember, there's too much unknown in the universe to take a break from learning. Get out there and question everything.